So then why don't we jump back into the terminal, and I'll show you a couple of tunables to set on the machine, one of which through a TuneD profile.
Sounds good.
And then we can maybe do a little bit of whiteboarding in a bit too. All right, so I'm currently set on deadline. So bring it down to sys block SDA Q. One of the other settings that we can change through TuneD is this read ahead KB. So read ahead is when we are looking up a piece of data that we need to read off of the disk. We'll not only read that piece of data, we'll actually read a certain amount beyond that too. So think about if you're retrieving a file and that file is, I don't know, 8, 9 megabytes. So you're requesting the first block of that file. What's the likelihood that you're going to request the next block and the next block after that and the next block after that to get this 8 or 9 meg file into memory? It's pretty high, right? If you're working with that file, you probably need the whole thing. And so the read ahead KB is when I receive a block request, I'm not only going to read just that block, I'm going to go ahead and ask the disk to read and send back a segment of data, this many kilobytes of data. And so on this system, that's 4K. I'm sorry, 4096K. So it's about 4 meg. So I'm going to read the piece of data, and then it is 4K. I'm going to read 4K in addition to that, thinking that the next disk IO request is probably going to be the next block anyway, and I'll have it in cache, right? Because I read it ahead. And so when you want to change this value, it's because you know that you're working with larger files. If you know you're working with larger files and you're going to be doing disk IO requests to read large files, then if you increase your read ahead buffer, then you'll get more of them in one go, and we can read them out of cache instead of having to actually return to the disk device and get more data. If you know that you're dealing with very small files, you could actually tune this back the other way and make it read less, because what would happen is you'd read a bunch of data on the next bit of the disk device, but because you're dealing with very small files, maybe that extra data we're reading isn't useful. We're spending a bunch of time retrieving it and then not utilizing it because we don't need it. And so that's the choice that you make here with read ahead. So how much should you read? So we could do something like echo 8192 into it. All right, so now we have live changed our read ahead kilobytes to be double. So I'm expecting larger files, and so I'm going to read more of them at a go because I'm expecting that I'll actually have that in cache and I'll need it anyway, so I'll just go ahead and read it in advance. If I was actually dealing with a lot of small files, this could hurt my performance because I'd be doing this extra work of reading the data, but then just trashing it and not actually using it. All right, so how do we make this a permanent change? So in the disk plugin for TuneD, so I'll go to my TuneD profile that I made. In this disk section, I can put read ahead equals A192. Oops, and I have that backwards. Equals greater than. All right, so now whenever I apply the virtual guest mine profile, not only will I get MQ deadline, but I'll also get this larger read ahead size applied automatically. The disk tunables, though, that's probably the most useful one in TuneD natively. The rest of them that we're going to talk about will actually have to create a shell script to go in and re-execute the changes to the ones that we're going to make. So here in the disk queue, there's this directory called iosched. And these are all the tunables that are for my chosen disk scheduler. So I'm currently running MQ deadline, and the two ones of note are the read expire and write expire. All right, these numbers are in milliseconds. And you'll notice that reads have a much lower expiration time than writes. And what it says is if we queue up our disk reads and writes, we don't want to completely starve out the system from doing a certain type of IO operation, so we have these expire times on them. So we'll queue them up, and if a read has been sitting in the queue for longer than 500 milliseconds, its expire time has been reached, and it will get automatically promoted to the front of the queue to be the next thing done. And the same thing can happen if they've been sitting there for 5,000 milliseconds or 5 seconds, they will expire and they will be promoted to be the next thing done on the IO queue. And so you can see by this differential in times that if a read has been sitting there for a while, it gets promoted. But the writes can be sitting there for 10 times longer before they get promoted to the front. All right. And so that's how we're preferencing reads to happen with MQ deadline versus writes. We're willing to hold the writes for longer. And so you can do things like, I could make that 50,000 milliseconds. And now we're going to hold them for 50 seconds before I promote them to be the front because they've been sitting for 2
Which sounds like a terrible idea, but maybe there's a reason for it.
So remember, the danger with writes is if you lose power, you lose the data. So if you're not really worried about something sitting there for 50 seconds because you're pretty consistently, your storage is battery backed or what have you, you can hold them for longer and it's probably okay. It will use more memory, right? Because you have to store them in memory to hold them. But this way we can hold them for even longer and we can push the reads out faster because they will always be preferential.
A slow read could more negatively impact the actual performance of an application though, right? So that would be probably one good reason why you would want a shorter read timeout than a write timeout.
And that's exactly
expire,
the case,
I should say, not timeout.
Right? Because if somebody actually looks at this data that we're waiting to write and actually wants to access it again, it's already in memory. So thanks to the Linux kernel page cache, you can get that data back very quickly because it has not yet been purged to disk. So that's another mystery, page cache. We can do that on another episode. But we're holding these for a lot longer, right? The other thing is if your disk is not super full of transactions, we're not just going to hold it for 50 seconds and not do anything. We'll go ahead and be doing disk transactions to empty out the queue. So this is really just like setting a timeout where it automatically gets promoted to the front of the queue versus being held and pushed back down in the queue because we have somebody else that's like our VIP person that we want towards the front of the line. All right, one other one that's turned on by default, front merges. So as we're queuing up our IO, if we find that there's an IO request that comes in that's adjacent to an IO request that's earlier in the queue, we'll go ahead and pull it in and put it there with its friend in the queue. And you've probably seen this in real life, right? Where you're like waiting in a line and then somebody walks up and is like, oh, hey, and they start talking to their friend in line.
And they're in line. Yeah.
Right. That's what we're doing, but with disk IO. So it's like, well, you're already going to be in that part of the disk anyway. And since the disk is already reading from that area, we might as well just do all the things at once.
Right.
And so that's what front merging does, is it allows them to be pushed earlier, even though their expiration time may not have been met.
It's the while we're here methodology.
Exactly. Now, I do feel compelled to also tell you that there's a little bit of difference between disk storage too. So where this was like super important, front merging was super important, was rotational disks. Because if you were going to read this piece of data later and it was further back in the queue, you had to wait for that like platter to spin all the way back around again so you could pick it up. And so by merging the two together, that way you could pick it up when the disk came around one time. This is less important. Because with SSDs, we're just like sending
'Cause there's
requests to the
no-
SSD, and it just like puts it randomly in some memory buffer.
There's no cost due to physical seek time anymore. Now it's just an address that it
Correct.
calls.
Right. And so front merges is less important if you know your disk storage backend. And in fact, because front merging is like taking somebody's read request that happened later on the system and promoting it in front of other things, this may be a place where if you disable it, you might see some beneficial performance because you're making those later requests wait until later. And you're servicing those requests and not like delaying any requests that may have been serviced or were placed earlier. So that might be something where we could like toggle that to a 0 and see if that changes our IO workload, but only if you're using SSDs or some kind of in-memory
Right.
in-memory storage in the back
Right.
end. All right. Cool.